projected out, is that still big enough?
We'll start in 1 minute. Today we start a new section, 8.1, on simplifying expressions with roots. Whatever that means. In section 8.1, we'll try to come to an understanding about what are called radical expressions. You probably have seen this symbol before. This symbol is referred to as a radical sign. The number or the algebraic expression inside the radical is called the radicand. For example, the radicand of this, we have the radical sign with the number 7 on the inside. The radicand is 7. Another example, if you have the radicand with x inside, the radicand is x. In general, if n is a positive integer, then this symbol, notice there's an n in that, I don't know what the term is for that little space, but there's an n and the radical sign. We refer to the n as the index. So a radical with index n is a positive integer. When the index of the radical is n equals 2, the radical sign can be written this way. You can put the integer 2 there, or you can leave the 2 out. Either way, it's what is called the square root. Okay, so to reiterate, if the index n of a radical is not written, then it is understood that the index is n equals 2. So this radical is equivalent to this radical. This one does not show the index 2. This one does show the index 2. But those mean exactly the same thing. Okay, if we let a be a number, then the radical with index 2 and radicand a is referred to as the principal square root of a. You can think of the principal square root of a as the positive square root of a. It's positive because there's not a negative sign in front of it. Okay, so the square root of a is equal to the number whose square is a. So in symbols, that means if the square root of a is equal to m, then the number a is equal to m squared, or m to the second power. So chances are you know some things about the square root already, but we're going to eventually get into radicands with higher indexes. Okay, but first we'll work with square roots, and then afterwards radicals with higher indexes. But when we work with square roots, it's helpful to know what the perfect square whole numbers are. So we will review the perfect square whole numbers. The perfect square whole numbers are found by squaring whole numbers. So in case there's any question about what the whole numbers are, what are the whole numbers? Well, the smallest whole number is 0. And then the next whole number after that is 1. And the next whole number after that is 2, and so on. So the whole numbers consist of the positive integers and 0. Okay, and the perfect square whole numbers are found by squaring whole numbers. Square roots of perfect square whole numbers simplify to whole numbers. For example, the square root of 49 is equal to 7, since 7 to the second power equals 49, which is a perfect square whole number. So we refer to 49 as a perfect square whole number because its square root is a whole number, which is the whole number 7. Okay, being familiar with lots of perfect square whole numbers is useful. Here is a short list. Well, there are infinitely many perfect square whole numbers, but the more familiar you can become with the ones up through, say, 900, that will make life easier. So work on a few at a time and then branch out after that. Okay, let's move on to the next page. So we will evaluate or simplify the following square roots. The principal square root of 25, well, it's the principal square root, so the answer has to be a positive whole number. Well, 25 is a perfect square. The principal square root of 25 is 5. The principal square root of 169, 169 is a perfect square. The principal square root of 169 is positive 13. And the principal square root of 289. So what's that one? See if anybody's awake. What's the principal square root of 289? So a hint is 289 is a perfect square. So what number would you have to raise to the second power to get 289? Okay, I got an answer online, 17. So if you ever need to search for a square root and you don't have a calculator, well, you could use better known square roots or square roots that are easier to evaluate. So the square root of 289, that has to be between the square root of 100 and the square root of 400. The square root of 100 is 10. And the square root of 400 is 20 because 20 times 20 is 400. So this narrows down where you have to look, somewhere between 10 and 20. Or it might just be easier to memorize that the square root of 289 is 17. Hey, the square root of 361, well, 361 is a perfect square. It has to be less than 20 because the square root of 361 is less than the square root of 400. So this one, the square root of 361 is 19. Okay, the next sentence. Note that the square root of negative 100 is not a real number, since there is no real number whose square is negative 100. If you square a positive number, you get a positive number. If you square a negative number, you also get a positive number. If you square 0, you get 0. And so the square root of negative 100 is not a real number. It is a number, but it's not a real number. Later on this semester, we'll learn how to handle the square roots of negative numbers. So to reiterate what I was saying, by definition, the square root of negative 100 is equal to m if m squared equals negative 100. And so m is not a real number since the square of any real number is not a negative number. Okay, and the square root of negative 100 is a number, it's just not a real number. Okay, that leads us to this definition. If we let x be a real number, then the square root of x squared is equal to the absolute value of x. So the reason that we need the absolute values in this definition is the case where if x is negative, x squared is positive, and the positive square root of a positive number must be positive, so we have to put the absolute value symbols around x. Okay, so a real number x can be positive, negative, or 0. If x is less than 0, that means x is negative. Then x squared is greater than 0, and the principal or positive square root of x squared is positive. So that is, if x is less than 0, the square root of x squared is equal to the absolute value of x. Okay, so now we'll move on to the next level. Variables with exponents that are multiples of 2 are perfect squares. The multiples of 2 are even integers. So the multiples of 2 are just 2, 4, 6, 8, 10, 12, 14, and so on. Okay, so next we'll learn how to simplify square roots of perfect squares with variables. Okay, so let x be a real number. Then if you raise x to a whole number that is even, those are considered perfect squares. So x to the second, x to the fourth, x to the sixth, and so on. Those are considered perfect squares because each of those exponents is a multiple of 2. And since they are perfect squares, square roots of perfect squares can be simplified to an expression without the radical symbol. So here are a few examples. The square root of x squared is equal to the absolute value of x. The square root of x to the fourth is equal to x to the second. Notice I didn't put the absolute value symbols around x, and that's because x squared is not negative even if x is negative. It would not be incorrect to put the absolute value symbols around x to the second, but it's not necessary when you're squaring a number. Okay, then the square root of x to the sixth is the absolute value of x to the third. This time the absolute value symbols are required because if x is negative, then x to the third is negative. So you have to take the absolute value of the negative. Okay, the next one, the principal square root of x to the eighth is just x to the fourth. The absolute value symbols are not required again. And then the next example, the square root of x to the 10th is equal to the absolute value of x to the 5th. Okay, note that, for example, when evaluating the square root of x to the 8th, the absolute value symbols are not required to enclose x to the 4th because x to the 4th is greater than 0 even if x is less than 0. So even though the absolute value symbols are not required around x to the 4th, you can still write the absolute values around x to the 4th. So it isn't incorrect to write the square root of x to the 8th equals the absolute value of x to the 4th, because the absolute value of x to the 4th is equal to x to the 4th. Okay, let's move on to the next page. Okay, if we assume that x is a positive real number, and most of the time in Newton, when you're doing the homework in Newton, the x will be considered a positive real number. Make sure you read the directions. So if we assume that x is already a positive number, then we can say that the square root of x squared equals x. So the absolute values aren't required if it is assumed that x is greater than 0. Okay, so if we consider how to simplify the square root of the perfect square x to the 18th, recall that the index of the square root is n equals 2. Since the exponent 18 is a multiple of 2, we can divide 18 by 2 to get 9, and then simplify the square root of x to the 18th to be equal to x to the 9th. So remember that we are, just to remind you, we're assuming that x is already positive, so that the absolute value is not required. Okay, so here's another example. Suppose you have the square root of x to the 214th. And we'll assume that x is greater than 0 again. So let's see if we understand how to simplify something like the square root of x to the 214th. The exponent 214 is an even integer because the last digit 4 is even. 214 is even. So we can simplify that to x to the 214 divided by 2, or x to the 107. So we note that we divide the exponent 214 by the index. So 2 is the index of the square root. 214 is the exponent on the variable. Okay, so now we'll go on to the next level. Now we will discuss radical signs with higher indexes. Okay, the radical sign with index n equals 3 looks like this. We have the radical symbol, and the positive integer 3 is in that part of the radical. So if you have a radical with index 3, this is referred to as the cube root. So now if we let a be a number, then the cube root of a is equal to the number whose cube is a. So remember, when you cube something, you raise it to the third power. So what that means is if the cube root of a is equal to m, then a is equal to m to the third. Okay, so let's review some of the perfect cube whole numbers. The perfect cube whole numbers are found by cubing whole numbers. So 1 to the third is 1. That's a perfect cube. 2 to the third equals 8. 3 to the third equals 27. 4 to the third equals 64, and so on. So those are perfect cubes. Okay, so cube roots of perfect cube whole numbers simplify to whole numbers. Here's an example. The cube root of 8 is equal to 2, since 2 to the third equals 8. And 8 is a perfect cube whole number. Being familiar with lots of perfect cube whole numbers is useful. Here's a short list. So these are the first few perfect cube whole numbers. It shouldn't be that hard to memorize the perfect cube whole numbers up through 1,000. And we'll see a lot of those fairly frequently. So 1,000 is pretty easy to remember. That's just 10 to the third power, 10 times 10 times 10. And the other ones you could get familiar with practice. So there's only 10 of them. Okay, let's move on to the next page. So evaluate or simplify the following cube roots. Simplify the cubed root of 64. So what's that equal to?
4.
Yeah, the cube root of 64 is equal to 4. Since 4 to the third power equals 64. So 64 is not only a perfect square, It's also a perfect cube. Okay, then the cubed root of 343. So 343 is a perfect cube. So the cubed root of 343 is equal to 7. Since 7 to the third is 343. Okay, I'll let you answer the next one. The cubed root of negative 125. So if you know the answer to that, go ahead and type it in. Okay, the answer is negative 5. Because if you raise the number negative 5 to the third, so remember what this means. We have negative 5 in parentheses to the third. That means negative 5 times negative 5 times negative 5. And a negative times a negative times a negative is negative, so we get negative 125. Okay, so cube roots are different than square roots. The square root of a negative number is not a real number, but the cube root of a negative number is a negative number, a negative real number. Okay, so that's a difference between square roots and cube roots that you'll have to make sure you understand. Okay, then our next example, the cubed root of negative 1,000.
Negative 10.
Yeah, negative 10. If you raise the number negative 10 to the third power, that means negative 10 times negative 10 times negative 10, which is negative 1,000. All right, let's move on to the variables with exponents. Variables with exponents that are multiples of 3 are perfect cubes. So here are a few examples of perfect cubes. X to the third, x to the sixth, x to the ninth, x to the 12th, x to the 15th, x to the 18th, x to the 21st, and so on. If the exponent is a multiple of 3, it's referred to as a perfect cube. Okay, so the cubed root of x to the third is x to the first. The cubed root of x to the sixth is x to the second. The cubed root of x to the ninth is equal to x to the third. The cubed root of x to the 12th is equal to x to the fourth. So note one other difference between a square root and a cube root. For a cube root, x can be positive or negative, and we never need the absolute value symbol for a cube root, because as we saw before, the cube root of a negative number is a negative number. Okay, so do you see the pattern on how to simplify cube roots of variables raised to exponents that are multiples of 3? So let's try this one, the cube root of x to the 102. Uh, 102 is a multiple of 3. So x to the 102 is considered a perfect cube. So how are we going to simplify the cube root of x to the 102? What should the exponent, what should that simplify to? Okay, I have a couple of answers online. It's x to the 102 divided by 3, which is 34, x to the 34th. Okay, note that's how we simplified, or that's how we can simplify the cube root of a variable term that is a perfect cube. When we simplify, we divide the exponent on the variable by the index. So in this first example, 3 divided by 3 is 1. The cube root of x to the 6th is x to the 6 divided by 3, or x to the 2nd, and so on. This last one, the cube root of x to the 102, simplifies to x to the 102 divided by 3. So that's the observation to make here. 102 divided by the index 3 is equal to 34. All right, the next sentence. In general, if the index of a radical is an even integer and the radicand is a negative real number, then it is not a real number. So there are higher indexes than 2 that are even integers. We'll see some of those here in a couple of minutes. But make sure that you absorb that. If the index of a radical is an even integer, so the even integers are 2, 4, 6, 8, and so on. So if the index is even and the radicand is negative, then that is not a real number. It's a number, it's just not a real number. Okay, on the other hand, if we have an index of a radical that is an odd integer, like we refer to them as positive odd integers. So 1, 3, 5, 7, and so on. So if the index is an odd integer and the radicand is a negative real number, then it is a negative real number. Okay, a couple of examples to reiterate the previous two sentences. The square root of negative 64 is not a real number. The index is 2 for a square root. And it's okay to write the index 2 if you want, but if you don't see the index, it's understood that the index is 2. So if the index is even and the radicand is negative, then it's a number that's not a real number. But on the other hand, if the index is odd, like 3, and the radicand is negative, then that's equal to a negative real number. In this case, the cubed root of negative 64 is equal to negative 4, since raising the number negative 4 to the third power equals negative 64. Okay, one more example, one more pair of examples. The fourth root of the number negative 81. This time the index is 4. But 4 is an even integer, so the fourth root of negative 81 is not a real number because the index is even and the radicand is negative. Okay, but if you have a radical with an index that's an odd integer like 5 and the radicand is negative, then this will simplify to a negative real number. In this case, the fifth root of negative 7,776 is equal to negative 6, since raising the number negative 6 to the fifth power is equal to negative 7,776. Okay, so make sure that you understand the difference between a radical with an even index compared to a radical with an odd index. Okay, let's try a few of these examples. The fourth root of 16. The index is 4. The radicand is positive 16. So it's equal to a positive real number. So how do we simplify the fourth root of 16? So this is referred to as the fourth root of 16. So that's equal to whatever you would have to raise to the fourth power to get 16. Yeah, 2 to the fourth is equal to 16. So the fourth root of 16 equals 2, since 2 to the fourth equals 16. Okay, then the one on the right, the fourth root of negative 16. So for now, we'll just analyze it in the following way. The index is even and the radicand is negative. Therefore,
Not a real number.
it's not a real number. This is non-real. It is a number, it's just not a real number. Okay, then the next one, the fifth root of 32. So the fifth root of 32. So 32 is a perfect fifth power. So the fifth root of 32 is equal to whatever you would have to raise to the fifth power to get 32.
2.
Yeah, 2. The fifth root of 32 is equal to 2, since 2 to the fifth is 32. Okay, the next one, the fifth root of negative 32. What's the fifth root of negative 32?
Negative 2. Negative 2.
Okay, the fifth root of negative 32 is equal to negative 2. So remember that if the index is odd, like 5, and the radicand is negative, then the fifth root of a negative is a negative number, in this case, negative 2. And this is true because if you raise the number negative 2 to the fifth, that's equal to negative 32. All right, the next one, the sixth root of 729. So we read this as the sixth root of 729. So does that simplify to a positive integer? Okay, it does. It does simplify to a positive integer. But it can't be very big. If you think about the sixth root of 1 million, that's only 10. So the sixth root of 729 should be smaller than 10. So it wouldn't take that long to figure out what it is. So I'll let you figure that out, and you can tell me what it is.
3.
Yeah, so type it in on the online when you find it. The sixth root of 729. Okay, so there's one. 3 to the sixth is equal to 729. So the sixth root of 729 is 3. Since 3 to the sixth is 729. So 3 is not a very big number. Okay, what about the sixth root of negative 729?
It's not real.
Yeah, it's non-real. This one is non-real. It's non-real because the index is an even integer. 6 is an even integer, and the radicand is negative, so it's non-real. Okay, the seventh root of 78,125. Can't be very big.
Five.
Yeah, this one's 5. Since 5 to the 7th is 78,125. And the seventh root of negative 78,125. Well, the index is odd. The integrand is negative, so this is -5. Okay, we're out of time, so go ahead and sign in for attendance.
Zero.